excess pressure across the free surface of liquid. So we have seen the different shapes of liquid in a capillary. One is a concave shape, another convex, and third is a plane. So why this produces that we see today? This is because of the pressure near the free surface of liquid and pressure present above the free surface of a liquid. We consider the 2 points near the free surface of a liquid, one just above the free surface and one just below the free surface of a liquid. Consider 2 points A and B. Point A is just above the free surface of liquid and point B just below the free surface of a liquid. So pressure at point A is atmospheric pressure because point A is in air and around it all air particles are present. They apply the pressure on the surface of a liquid. Because of the pressure, force at A acting on the free surface of a liquid, and the force at A is a downward force denoted by Fa bar due to the atmospheric pressure. Now the three cases of liquid surface. First case, plane liquid surface. Surface is remain as a plane, no concave, no convex shape, only plane shape is there. On the free surface of liquid, surface tension present, and that surface tension apply the force, we denote that Ft bar. In this case, resultant force due to the surface tension of a liquid on a molecule B is 0. So this liquid surface, this surface tension of pre-liquid surface does not apply any force on this point B, or the pressure at B must be equal to the pressure at A, and because of that liquid surface remain plane in a shape. If there is a pressure difference at point A and point B, then this free surface does not remain a plane. In this first case, pressure at A is equal to pressure at B. Because of that, free liquid surface remain plane in a shape. Second case, if a liquid surface convex in a shape in this way. So convex liquid surface. Ft bar, again the resultant force due to the surface tension on molecule at B is acting vertically downward. So because of this free surface tension, that surface tension apply the force on a molecule B which is in downward direction. As a force act in downward direction, pressure at B greater than the pressure at A. At pressure at B is more than the pressure at point A. The pressure on the concave side, that is inside the liquid, is greater, and therefore the liquid surface takes a convex shape. Third case, concave liquid surface. We consider this case. Ft bar, resultant force due to the surface tension on molecule at B is acting vertically upward. Now here the surface tension act in upward direction. Therefore pressure at B is less than the pressure at A. So upper pressure is more and below pressure is low. And because of that, pressure on concave side, that is outside liquid, is greater, and liquid surface take a concave shape, that is pushing in downward direction. That means here you consider the pressure at point A and pressure at point B. When the pressure at point A and pressure at point B is equal, then the liquid surface take a plane shape. If the pressure at point B is greater than the pressure at A, that pressure at a point inside the liquid is greater than the pressure at a point which present in air. In this case, the liquid surface takes a convex shape. And if pressure at point inside the liquid is less than the pressure outside the free surface of liquid, then the liquid surface take a concave shape. Laplace law of spherical membrane. It is also known as explanation of formation of a drop and bubble. Due to a surface tension, free liquid drops and bubbles are spherical in shape. As a liquid drop spherical in shape, the inside pressure will be greater than the outside pressure. In previous topic we have seen the convex shape, the pressure outside, that means at point A, and pressure at B. Pressure at B, that is PB, is greater than the PA, and because of that it takes convex shapes. So for spherical also it is totally convex. So inside pressure is greater than the outside pressure. Let P0 is equal to outside pressure, Pi inside pressure. The radius of a drop increases from small r to r plus delta r. Now we increase the inside pressure, and because of that its shape increases and it takes a new shape which shown by the dotted line. So distance increase as a delta r, that means radius increase as a delta r. Initial surface area, we know the formula for sphere, that is 4 pi r square. So initial surface area AI is equal to 4 pi r square. Final surface area, that means surface area of this dotted sphere, AR or AF, which is equal to 4 pi. Now radius changes, r plus delta r whole bracket square. Expand this square, 4 pi inside bracket r square plus 2r into delta r plus delta r square, bracket complete. Delta r is very small, so if you take its square it is also very small, so we neglect the delta r square. After neglecting and opening the bracket, we get AF is equal to 4 pi r square plus 8 pi r into delta r. So excess created surface area. So excess created surface area is equal to final surface area minus initial surface area, which is equal to 8 pi r delta r. By substituting the value, we get the value 8 pi r delta r. We calculate the work done while expanding the spherical bubble. So we know the formula for work done. Work done is nothing but surface tension into change in area. This is one formula. Also we know the second formula. Work done is nothing but excess force into displacement. We consider both the formula. First formula, work done is equal to surface tension T and change in surface area, that is delta A. Substitute the value of delta A, that is 8 pi r delta r. We get the equation 1. The second formula, work done is equal to excess force into delta r, that is applied force, into change in displacement. Excess force is nothing but pressure into initial area, because we know the pressure is equal to F upon A. From that we have calculated the force. So work done is equal to excess pressure into initial area into delta R. So excess pressure, that means that is inside pressure minus outside pressure. So Pi minus P0 into initial area into delta R. Substitute the value of initial area 4 pi r square into delta R. We get the equation number 2. Equation 1 and the 2 are the same equation. Equate both. Inside bracket Pi, that is inside pressure, minus P0 outside pressure, bracket complete, into 4 pi r square delta R is equal to T 8 pi r into delta R. Cancel the terms which are possible. Then we get Pi minus P0 is equal to 2T divided by R, called as Laplace law of a spherical membrane. Pi, pressure inside the spherical drop, minus P0, that is pressure outside the spherical drop. In case of soap bubble, there are the two free surfaces in contact with air, because in spherical bubble inside is also air, outside is also air. So both side air present, and because of that inside surface area and outside surface area both we consider. In that case, total increase in surface area is twice inside bracket 8 pi r into delta R. Also work done is twice inside bracket 8 pi r into delta R into T, and therefore the excess pressure Pi minus P0 is equal to 4T divided by R, that is twice than the spherical drop, because in a drop inside is complete liquid, outside is air. And for soap bubble, inside also air present and outside also air present. So we consider both the surface areas. थोडक्यात लॅप्लॉस लॉ म्हणजे ड्रॉपमधील आतील प्रेशर आणि ड्रॉपच्या बाहेर असणारं प्रेशर यांच्यातील फरक काढणारा जो फॉर्म्युला आहे त्याला म्हटलं जातं लॅप्लॉस लॉ. पी आय म्हणजे आतून असणारं प्रेशर त्या ड्रॉपमधलं, आणि P0 म्हणजे त्या ड्रॉपवर बाहेरून लागणारं प्रेशर. या दोघांचा डिफरन्स, त्याचं सूत्र तुम्ही 2T डिवाइड बाय R कॅल्क्युलेट केलं आहे, आणि त्यालाच म्हटलं जातं लॅप्लॉस लॉ फॉर स्फेरिकल मेम्ब्रेन. लिक्विड ड्रॉपमध्ये आतून सगळं लिक्विड आहे. इथलं प्रेशर पी आहे, बाहेर एअर आहे, एअरचं प्रेशर P0 दिसतं. पी आय या स्फेरिकल शेप असल्यामुळे पी आयची किंमत जास्त असते, P0ची कमी असते, म्हणून पी आय मायनस P0. आता लिक्विड ड्रॉपच्या ऐवजी सोप बबल जर घेतला तर सोप बबल घेतला म्हणजे आतल्या बाजूला हवा आहे आणि बाहेरच्या बाजूला हवा आहे, म्हणजे हवेच्या संपर्कात या बबलचे दोन सरफेसेस आले, एक आतलाही सरफेस आला आणि बाहेरचाही सरफेस आला. म्हणून या दोघांवर होणारा जो प्रेशरचा डिफरन्स मला काढायचा होता, म्हणजे आतल्या सरफेसवर आतून जी हवा प्रेशर लावणारी तोही P0 झाला, बाहेरून जी लावणारे तेही P0 झालं, आणि दोघांच्यामध्ये हे जे काही सोप बबलची लेअर आहे ती आतल्या बाजूला प्रेशर लावते आणि बाहेरच्या बाजूला प्रेशर लावते, म्हणून इथं आपण 2 घेतलेला आहे मल्टिप्लाय करून. पण त्या केसमध्ये एक्सेस प्रेशरसुद्धा दुप्पट झालेलं तुम्हाला दिसून येतं. कॅपिलरी. Capillary is nothing but a glass tube having a very small bore. That glass tube is known as a capillary. A tube having a bore of very small diameter and open at both ends is also called as a capillary, or a tube having very small bore or fine bore and open at both ends is called as capillary. Generally, it is made up of using the glass. कॅपलरी म्हणजे काही नसून एक काचेची नळी जिला आरपार एक बारीक छिद्र असतं तिला म्हणलं जातं कॅपिलरी. कॅपिलॅरिटी, the phenomenon of rise or fall of a liquid inside the capillary tube when capillary tube dip in the liquid is called capillarity. In the same glass tube, now we say the capillary, whose one end is deep in water, then some water rises in the capillary. Or if you dip that same capillary in a mercury, then instead of rising the mercury in a capillary, it get fall inside the capillary. So this rise or fall of a liquid in a capillary, that phenomenon is known as capillarity. याच काचेच्या नळीचं एक टोक तुम्ही पाण्यात बुडवलं तर पाण्याच्या सरफेसपासून कॅपिलरीमध्ये काही उंचीपर्यंत पाणी वर चढलेलं दिसून येतं. त्या सेम कॅपिलरीचं जर तुम्ही मर्क्युरीमध्ये बुडवली किंवा तिचं एक टोक मर्क्युरीमध्ये बुडवलं तर मर्क्युरी मात्र काचेच्या नळीत वर चढलेला दिसत नाही, तर त्या काचेच्या नळीत खाली गेलेला दिसून येतो. म्हणून इथं आपण म्हणलं राईज ऑर फॉल ऑफ अ लिक्विड. मग ते लिक्विडनुसार ते अवलंबून असेल. काहींच्या केसमध्ये कॅपिलरीमध्ये पाणी वर चढेल, काहींच्या केसमध्ये खाली जाईल. सो इन सम केस ऑफ liquid rises in a capillary, or in some case it falls in the capillary, and that phenomenon is known as a capillarity. So we say some examples. When water is spread on tiles and then we use a cloth to remove the water from the tiles, so that cloth gets suck that water because of this capillarity action. Or in case of trees, from the root of trees, sap and water rises up to the topmost leaves in the tree. This is because of a capillarity action. Blotting paper absorb the ink, or any paper absorb the ink. That process is because of the capillary action. Oil rises up the wick of the lamp. Nowadays we are not using the lamp. Still near to your God you are lighting some lamps where we see that the cotton wick absorb the oil and that oil move towards the lightning portion. That process is because of the capillarity. Explanation of capillarity action. We see the derivation for both the case capillary rise and capillary fall. First we see the capillary rise and why this takes place. Then we see the capillary fall. I will explain only the capillary rise and you write your own as capillary fall explanation. Both explanations are similar, only some words are different. That words are marked by the red pen. Only you change that red words using the other words that also shown to you and you write capillary fall your own. Capillary rise. We consider 4 points. 1. Inside the capillary, above the free surface present in the capillary. Second, also inside the capillary but just below the free surface of liquid in a capillary. Third point, above the free surface of a liquid but outside the capillary. Fourth point, also outside the capillary but in a liquid near the free surface of a liquid. Let a glass capillary tube is dipped into the liquid which wet the capillary. Consider the situation before the movement of water inside the capillary. This is the initial condition. Now high water rises in a capillary, that part we are observing. So whatever 3 points, 4 points, A point just above the concave surface inside the capillary, B point just below the concave surface inside the capillary, C point just above the plane surface outside the capillary, D point just below the plane surface outside the capillary. PA, PB, PC and PD gives you the pressure at point A, B and C. We are considering these 4 points. PA is greater than PB because the pressure on concave surface is always greater than the convex surface. So PA is greater than PB. But PA is equal to PC because both are atmospheric points. So pressure at atmospheric point is same. Also PC is equal to PD, points above and below the plane surface. When the surface is a plane, we know the pressure above the plane surface and pressure at a point inside the plane below the plane surface is the same. So PC is equal to PD. From these 2 points, we may write PA, which is equal to PC, is equal to PD. Now we consider the first point, PA greater than PB. So PA is greater than PB. Naturally, PD greater than PB. That means the pressure at a point D, which is inside the liquid, and pressure at a point B, which is also inside the liquid, is different. So pressure at D is more than the pressure at B. That means the pressure at B is less. And because of Pascal's law, pressure inside every point inside the liquid must be the same. So to balance this pressure, the liquid start rising in the capillary. So it rises inside the capillary, up to which when the pressure at D must be equal to pressure at B. So PD greater than PB, therefore the liquid flows into the capillary and rises above till the PB is equal to PD. Using the same concept, you write the second portion, that is a capillary fall, by changing the word does not wet, mercury, convex, concave, convex, PA less than PB, PA less than PB, that implies PD is less than PB.